Okay, thanks very much. Thanks for having me. And also thanks for Lindsay for her talk, which was very interesting. And yes, I would like to talk about lunar occultation observations, in particular to radio sources. And the outline of my talk is that I'll first talk about what are lunar occultations anyway. Then how do you predict those events? And what are the possible observation strategies that you can choose from? And then I would like to show some of the results that we had on lunar occultation. So let's get started on what are lunar occultations. Actually, that's something that you hopefully will be able to experience today. Uh, the sun will be covered by the moon. That's so indeed a lunar occultation of the sun. You don't call it lunar occultation, you call it eclipse, but anyway, it's physically the same thing. The moon gets in the way of your line of sight to a object. So how, yeah, that's repeating the same thing. For in the radio case or in any case, the lunar occultation can happen for objects which are close to the ecliptic. Obviously, if it's far away from the ecliptic, it's never going to happen. And as you know and experience again today, it's a rare event. It doesn't come frequently. For a specific object, you would typically take quite some time, could be years or even decades, or sometimes could be once in a lifetime event. So we were looking at possible events that we could observe with our radio telescope, with our 25-meter dish. All observations were done at 1420 megahertz. So what you try to do is to catch an event where a radio source disappears behind the moon. So how do you predict that? First point is, of course, you need to calculate the position of the moon. You calculate the position of the radio source. And then what you need to do also take into account that is the apparent diameter of the moon is dependent on what the moon's distance is. So it changes. So you need to take that into account. And what you then do is you calculate the angular distance between the moon and the radio source. You can do that for different times. You do it in small increments. You iterate over time and look if the angular distance between the object and the moon is smaller than the radius, the apparent radius of the moon, then there's an occultation. And this can be done. Today, we are using PyFM, or you could also use AstroPy, where you can do all these calculations. What you need to do is to have exact source positions. And today, for the objects that are of interest, all those are very well known. And in our case, we took it from the astronomical database. So what you can do is sort of look at radio sources that are sufficiently bright, that are close to the ecliptic, and then just let your computer run and see if there is a potential occultation. And that's how you predict them. The two expressions, the disappearance, so when the object is covered by the moon, the moment that is called the immersion, and when it comes back, it's called immersion. And with today's knowledge of the precise positions, this can be calculated very accurately. So typically you're better than 1 second in predicting when such a thing appears. So that's essentially what we've been doing for a number of objects. Now, there are different possibilities how you observe it, and both or all three of them have advantages and disadvantages. I quickly go through that. The first idea would be to put the telescope at the position where the immersion will occur, and then after that, put it at the position where the immersion occurs. The advantage there is that while you try to capture the immersion and the immersion, you don't change the position of the telescope, hence you don't change the thermal background. So you have a stable thermal background. When you every time you move the telescope, the thermal background from the ground can change a bit, and that gives you a change in the signal. However, there's a disadvantage. You need to switch position. So you put your telescope to the point of immersion, you observe things happening, and then you move the telescope to the immersion point and then wait until it comes back. That's a disadvantage because you don't see what's happening in between. A second approach would be to put the telescope at the rim of the moon, at the point where the immersion or immersion occurs. That has an advantage, that because your telescope beam and the moon position remains always the same, the contribution of the signal from the moon remains constant. So you're always looking at the same part of the moon, and that remains constant. Again, the same disadvantage is that you need to switch position. So you first have to go to the immersion point and then to the immersion point. That's a disadvantage. The third option is to track the object which will be obscured. So you put your telescope onto the target which will be obscured and then track it. What will happen then is you have a constant contribution from the signal from the source that remains always the same until the moment of immersion. You don't have to switch the position. You just keep tracking while the object is not visible, and then it will appear again. The disadvantage there is that you have a varying contribution of the signal from the moon. That is simply, and we'll see it in a moment, as the moon approaches your observed object, it comes closer and closer, enters into the beam, and the signal will increase. And of course, then it's a strong variation of your signal. We have always been using the third possibility of doing it. We never tried the others. The problem there is you have only one chance. It happens, and you can't decide, let's do it over again and try the other technique. You just have to make a choice, and our choice has been to track the object, and we'll see the consequences of that. I cannot say that any of the, let's say, other possibilities are more or less advantageous. We just had to make a choice. All right. Having said and explained our observations strategy, let's go to the actual observations that we did. We have 3 objects where we have so far observed the lunar occultation. One of them is the Crab Nebula, which is a well-known supernova remnant. The interesting thing about the Crab Nebula is that it has a fairly high flux density. So it's 900 Jansky roughly at 1400 megahertz. And that's pretty much the same as the thermal emission from the moon. So you have 2 objects which have essentially the same order of magnitude of signals that they deliver. And you should see a very distinct difference when the Crab Nebula disappears behind the moon. The observations were done in 2020, so actually 4 years ago, roughly. And typically what happens is that if there is a lunar occultation, a second or third comes within a fairly short distance, and then it's gone for quite a while. So we had 2 lunar occultations of the Crab Nebula in 2020 in March and July. These are the calculated times, and then we just went ahead and observed that. The observation, first of all, what we did also for this particular occultation, we calculated what would be the path of the desired object, in this case the Crab Nebula, with respect to the apparent diameter of the moon. So essentially it was a path which was looking like that. Hardly ever the object will hit the middle of the moon, so it's sort of passing not necessarily through the center, but that's typically sufficient to fully cover the object. So this was the March 3rd, and you can just imagine that we were sort of following, as we were tracking the object, we were following this path essentially, and then eventually it was hitting the moon. And on July 18th, just a different path that was followed then, just because it's a somewhat different scenario there. Okay, what did we observe? This is the recording of the overall signal. That's the total power signal. Actually, there are two, which you can see. These are our two polarizations, so we use both polarizations. Then you see a lot of stuff around here, which is unfortunate, the usual thing that you have RFI. Also here, this is a RFI spike. Same here, and lots of RFI over there. But still, there's a very distinct curve. The predicted times of the immersion and immersion are depicted here. So these are the expected times. And now you have to, or I have to explain, what is this curve all about? How does that come about? Now what happens there is, when you start here, essentially you have the signal from the Crab Nebula. It's a fairly strong source, so it's quite a signal. And what happens then is that, based on our observing strategy, that the moon approaches. So more and more you get additional signal from the moon. Yeah, so the overall signal rises. And then the crab disappears. And that's not a sudden disappearance, because the Crab Nebula is an extended object. It's not a very point object. It has a certain extension. So the Crab Nebula disappears, power drops. So, and this is essentially the power drop from 900 Jansky when the crab finally completely disappears. What then happens is that we are only seeing the moon, and we are seeing an increase of the signal just because we are seeing more of the moon. It's getting more and more into our beam, and then it starts to move out of our beam again, and the Crab Nebula comes up again. We're just rising there again as more and more of the Crab Nebula comes back behind the surface of the moon. And of course, then the same thing happens again, that the moon moves away from our beam. We still are tracking the Crab Nebula, so we continue to have the signal from the Crab Nebula, but the signal from the moon disappears. So this is essentially a very classical example of a lunar occultation that shows two sources of a similar magnitude. So you can change the moon. It has a 900 Jansky, but in this case, the Crab Nebula has about the same order of magnitude. We had a second observation. The different scenario here in July was that the moon, or the event happened very, very close to the horizon. So we had to go very deep with our telescope, which means that we were getting a lot of noise and also RFI from the ground, because we were just essentially looking almost to the ground. And this is why the signal is quite noisy here. And then, of course, the same thing happens at the predicted time. The Crab Nebula disappears, and then same curve of the moon as we're seeing more and more of the moon, and then we're getting out again. And here, fortunately, we're a bit further off from the horizon, as both rise from the moon and the Crab Nebula rise from the horizon, and we get a much cleaner signal here. Also, what you can see is that the curve is higher here than here. That is just the additional thermal radiation from the ground that we are getting. All right, so this is very much an interesting experiment. of course, things happen as expected. And now let's have a look at, this is just what I have explained. Then there's a fairly recent lunar occultation that we have observed. That's the Sagittarius R region. And I should start by saying a few things about Sagittarius R, because it's frequently related to as the center of our Milky Way. And that's actually not true. If you point a telescope of our size, like 25-meter dish, towards the galactic center, the signal, you'll see a strong signal there, but it's not from the galactic center. That's a frequent misunderstanding, because what you do see is essentially two radio sources called Sagittarius R West and Sagittarius R A East. And they just happen to be in the direction of the galactic center, but they are not at the galactic center. So they're somewhere along the line of sight. The actual galactic center, called Sagittarius A star, has only a minor contribution of 3 Jansky. So this is really quite negligible to the hundreds of Janskys that we have from those two sources. By the way, one of the sources is also a star-forming region, an H2 region, and then I think the other one is again, just like the Crab Nebula, a former exploded neutron star. We had events in December, on December 13th, for Sagittarius R East and West, just because they're very close to each other, very close in time. And then there was another one on the February 16th on both, and we observed both. This is showing the lunar occultation of the Sagittarius R region from February. So it was essentially the second observation. And you see a very similar curve, not as clear and not as noise-free as from the Crab Nebula, because it's not quite as strong. You see the same thing, that the signal drops at the time, the expected time of the disappearance of the two sources. They are so close to each other that we cannot distinguish that. And then they come up again. So it's the same behavior essentially as we have seen from the Crab Nebula. What is not depicted here in a sense is the moon, we had the same thing, that the moon was rising the signal and dropping here again. It was not as clear as for the Crab Nebula, but it was the same, in principle, the same thing. I should mention that that was a joint experiment also with the Dwingelo telescope. We did it simultaneously with our friends at the 25-meter dish in Dwingelo, and had similar results. All right. Then there is a third lunar occultation that we have observed, and that's a somewhat different story. In this case, it's a radio galaxy, 3C273. And this has a flux density of 45 Jansky. So we're talking about a much weaker source here. Just as a reminder, the moon has 900 Jansky. Crab Nebula has 900 Jansky. The galactic center is also in a couple of hundred Jansky range. Now we are talking about a 45 Jansky. So the effect is much smaller. So essentially what you have to observe is the disappearance of 45 Jansky against a background from the moon, which could be as high as 900 Jansky. Again, this was back in 2020. in July, October, and in January. So we had 3 events, which we in principle were able to observe. So that's what we did. And this is the curve which essentially is the best that we have. So I've picked that one from January 16th. And what we see, and you're already familiar with that, is that you have the approaching moon. And then you see a sudden drop. And that is, as we will see in a moment, the time of the immersion. And again, unlike in the Crab Nebula where you really drop down deep, in this case, it's a smaller drop. And then the moon gets more and more into the beam. There's some ugly RFI coming in here as well. Fortunately, RFI disappeared again, stopped before we had the immersion. And there, all of a sudden, 3C273 was back again. Okay. You can see the difference to the other lunar occultation, that this is a very sharp edge here, very sharp increase because it's a compact object. So let's zoom into these 2 parts here. So this is a detailed plot of the immersion, and here of the immersion. The calculated time are the lines again, the dotted lines again. And the scale here, this is in minutes and seconds. So we are talking about an event that's happening in the few 10 seconds, so 20 seconds maybe. Same here. And what you will observe is that there is a very distinct pattern here. So it's oscillating. It's not just a sudden rise, but it's an oscillating here. Same can be seen here, not quite as clear as at the immersion, but still you can see the principle here. The reason for that is that it is a very, very compact object, pretty much a point source. And what happens there is a diffraction at the edge. So what happens there is what will happen with a point source at an edge. So the point source approaches, you get some diffraction, and then you get a diffraction pattern, which sort of then gets higher in frequency and dies out. And this is exactly what you can see here. There's a oscillation here, and that dies out. This is a very interesting effect because it shows that it is a very compact object. You wouldn't see that if it would be more extended object like the Crab Nebula, where you don't see that. And this effect that it is the finding that it is a compact object was something that was done back in 1962, because observing the lunar occultation of 3C273 is a radio observation that is of great importance in the history of radio astronomy. Back in 1962, the nature of radio sources was only vaguely known. There was something they knew where it was known it was kind of small, compact, but the resolution was not good at the time. You didn't have interferometry. You couldn't resolve the object. And this was also the reason why there was hardly any chance to make a correlation between an optical observation and a radio observation. It was not known whether a radio source had an optical counterpart or vice versa. And this experiment that was done in 1962, where there was a prediction based on the, let's say, fairly coarse position of 3C 273. There were some calculations being done, and the idea was to observe that when that source disappears at the moon. That was a time when the Parkes telescope had just been finished, and it was actually, it was not quite ready yet, but they even had to go to a special measure to do that, because this occultation also happened when the source was very low on the horizon. So they had to change something temporarily on the telescope so that it could actually go so low on the horizon. But the importance of this experiment at the time was that it was the first time that a very precise localization could be achieved, because they could measure the time. When does it happen? The position of the moon was very precisely known. Now they could determine when exactly does the occultation happen. And from that, they could very precisely determine the position of that radio galaxy, which at the time was called a quasar. And what I have depicted here is the original recording, and you can also see the fringes here, very similar to what we have seen. There is and I highly recommend, if you have the time and the interest to look at that, there is a report on the whole story behind that on the Parkes website, where there's a lot of information, background information, the people involved, and all the things that were going on at the time. It's a very interesting reading, a lot of additional material. Since we have some time, maybe I can actually open that. Hopefully that will work. Let's see. I'm not sure whether that comes up. Did the website come up?
It has not.
It has not. So let me
see your PowerPoint.
Yeah, I probably need to.
There we go.
Can you see? Yeah, okay. Just a few things as an introduction, identifying the first quasar, the story behind that, reference to the original publication. What may be quite interesting, I mentioned how we do the calculation, comparing to how they did the calculation at the time. I find this quite interesting, I guess. Everything on paper and no computers, and anyway. So let me see that. How do I close that again? I want to get back to the website. Sorry about that. Let me just reopen that. Okay, just bear with me a second. Okay, so this is the picture I had shown. They had some better recordings as well. By the way, that was then at 410 megahertz. Now, I would like to show you one thing is, you see there is a dent here in the immersion. And they interpreted that as a structure within the radio galaxy, which indeed is true. These are the two jets that now we know these are the two jets, why it gives this additional dent there. So there was a lot of information all of a sudden, and as I said, what I really would recommend anyone who's interested to go onto this website and read about it. It's fun reading. The only caveat that I would say is that in this they mixed immersion and immersion. So this is actually the immersion, and this one is the immersion, and they keep confusing that in the website. But yeah, these things happen. Okay, let me go back to my slides. Okay, I hope the slides have come up again.
We see them.
Okay. Now what does not work? Yeah, now it works. Okay. The question is now, for anyone who might be interested in doing that, what is the next chance? Now, the trouble there is I can't give, just like for solar eclipses, they happen at certain positions and they are visible at certain places and they are not visible at other places. For us, for our position, the crab that we have observed will again be, there will be an occultation in March of 2030, so that's another 6 years to go. The Sagittarius R region, that's the first one is pretty soon for a lunar occultation in 26. However, it's extremely low on the horizon for us. And I have explained the trouble when you're low on the horizon, you get a lot of thermal background, you get RFI and so on. And in this case, I would say this is, we may be able to try it, but I'm not very hopeful. And then we would have to wait until 2042. Admittedly, I'm not planning that long. Then the famous 3C273 is again in June of 2038. So that's again quite a while, at least for our position. So I would encourage everybody to maybe do the calculation for their instrument. That might be doable also with smaller instruments if you talk about the Crab Nebula or something like that. For us, there's another occultation this year, and that is just a few Jansky. And if you consider what I have shown here, this is 45 Jansky, the drop. If that is much smaller, it's going to be a challenge. So this occultation for us this year in October and December, one can give it a try, but I'm not very confident that we will be able to see something. But anyway, I've chosen this topic because it's a good introduction for you for your lunar occultation of the sun later today. And I wish you have a clear sky, that you are actually able to observe it. In any case, if you set up a small radio telescope, you should be able to see a lunar occultation of the sun with a small radio telescope because there the intensities are big enough. And with that, thanks very much for your attention, and I'm happy to answer questions.
All right. Thank you very much. Great presentation. Any questions from anybody? You may have to speak loud with the laptop being so far away. Wolfgang, one question I had, are there benefits to doing this sort of observation at different frequencies?
There are some advantages, for example, to go to lower frequencies. If you, let's say, would go to 400 megahertz range, you have the benefit that the thermal emission from the moon is less. The moon is a thermal radiator, and it's substantially less at 400 megahertz. Our noise is dominated now, in this case, by the thermal emission of the moon. And at the same time, many of the objects I've been talking about are even brighter at 400 megahertz. So if we had the choice, we would have probably gone to 400 megahertz, just like the Parkes example. Also, that is more beneficial at 400 megahertz. So yeah, if you have the 400 megahertz capability, that would be a preferred frequency range.
Okay. Anything else? All right, I think we have it here. Any questions online? Silence is compliance.
Okay.